Welcome back to our channel Prash. Learning is fun. In this module, I am going to explain 10th state chapter Human Eye and Colorful World. We all know that we can see the objects only when light falls on the object. So the light falls on the object, this object will reflect the light. The reflected rays should reach our eye. Then we will be able to see the object. Can you read a book keeping very close to your eyes? No, it is not possible. The letters in the book appear blurred and our eyes get strained. Now slowly move the book backwards and then we will be able to read the books. This distance at which we can see an object comfortably and distinctly is called least distance of distinct vision. So to see an object comfortably and distinctly, we must hold it at a distance of 25 centimeters from our eyes. This distance is called least distance of distant vision. This varies from person to person and also with the age. Let us understand what is angle of vision. Observe this diagram. Here the rays are coming from the extreme ends of the object. So these rays are forming an angle at the eye. So if this angle is 60 degrees, then we will be able to see the complete object. So this angle we call it as angle of vision. If this angle is greater than 60 degrees, then we will be able to see only part of the object. So, if this angle is below 60 or equal to 60, we can see the whole object. And if the angle is above 60 degrees, then we can see only part of the object. So, this maximum angle at which we are able to see the whole object is called as angle of vision. For a healthy human being, this angle of vision is 60 degrees. This also varies from person to person and also with the age. The part of the human body which enables us to see the object and color around us is our eyes. Let us see the structure of human eye. Among all the parts, the lens, the pupil, iris, ciliary muscles and retina plays an important role in forming the image. The colored part of the eye is called the iris, which has a small hole in it. This is called pupil. Pupil appears black because light which is falling into the eyes will not come back. This pupil acts as a variable aperture. Iris helps the pupil to act as a variable aperture. Let us understand how the iris helps the pupil to act as a variable aperture. In dim light condition, the iris helps the pupil to expand so that more light enters into the eye. And in bright light condition, it makes the pupil to contract to prevent the excess light entering into the eye. The most important part of the eye which is responsible for the image formation is lens. This lens is hard in the middle and gradually becomes soft towards the outer edge. The light that enters into the lens forms an image on the retina. The distance between the lens and the retina is 2.5 centimeters. That means for our eye lens, the image distance is fixed and that is 2.5 centimeters. From the concepts of diffraction, we have learned that lens formula is 1 by f is equal to 1 by v minus 1 by v. That means here object distance and image distance are changing, but focal length remains constant. But just now we have studied that our eye lens has a fixed image distance. That means image distance is fixed. It means that there should be change in the focal length. Different object positions, the image distance remains constant only when focal length of the lens changes. Focal length of the lens depends upon the material and radii of curvature of the lens. So we need to change the focal length of the lens to get the same image distance for various object positions. This is possible when the eye lens is able to change its shape. It is the ciliary muscles which are attached to our eye lens helps to change the focal length by changing the radii of curvature of the eye lens. The ciliary muscles adjust the focal length in such a way that the image is formed on the retina and we can see the object clearly. This process of adjusting the focal length is called accommodation. The eye lens forms a real and inverted image of an object on the retina. This retina is a delicate membrane which contains about 125 millions of receptors called rods and cones. These rods and cones receive the light signals. Cones identify the color and rods identify the intensity of the light. These signals are transmitted to the brain through millions of optic nerve fibers. Thus, our brain is able to identify the object without losing the shape, size, and color. The lens present in our eye is a biconvex lens. Our lens can change its focal length to some extent only. When we are observing an object at far distance, then our eye lens adjusts its focal length to 2.5 centimeters and forms an image on retina. And when we are observing an object at nearer distance, then our eye lens adjusts its focal length to 2.27 centimeters and forms an image on retina. This means when the object is at infinity, our eye lens becomes thin and has a maximum focal length of 2.5 centimeters. And when the object is nearby, then our eye lens becomes thick and has a minimum focal length of 2.27 centimeters. If the position of an object is between infinity and a point of least distance of distant vision, then our eye lens adjusts its focal length between 2.5 cm to 2.27 cm so that a clear image forms on the retina. This ability of eye lens to change its focal length is called accommodation of lens. If our eye lens is not able to adjust the focal length, then we cannot see the objects clearly and comfortably. Thus, the vision becomes blur. When the vision becomes blurred, then we say that the person is suffering with defects of vision. There are mainly three common defects of vision. They are myopia, hypermetropia, presbyopia. Let us discuss about these defects in detail. Myopia, also called as nearsightedness. People with this defect of vision cannot see objects at long distances but can see objects at nearby distance clearly. For these people, the maximum focal length is less than 2.5 centimeters. When viewing a long distance object, parallel rays will fall on the lens and these rays converge and forms an image in front of the retina for a myopic eye. So, he can see a blur vision. So, when the object is moved closer to the lens, the image moves towards the retina and forms an image on the retina. So, this point we call it as far point. So, moving the object closer to the lens is not possible. So, what we will do? We will place a concave lens in front of the lens such that the parallel rays first falls on the concave lens and gets diverged, and the diverging rays will fall on our eye lens and gets converged and forms an image on the retina. When the concave lens is placed in front of the lens, it forms a virtual image at point F, which is called as far point. This image acts like an object for our eye lens and hence final image forms on the retina. The focal length of this biconcave lens must be f is equal to minus d. Minus indicates that the lens which we are using is a concave lens, where d is the distance of far point. For the exam point of view, defect of myopic eye is very important diagram, followed by correction of myopia. When we are viewing a nearby object, then our eye lens adjusts its focal length to 2.27 centimeters. If our eye lens is not able to adjust its focal length to 2.27 centimeters, then that defect we call it as hypermetropia. Hypermetropia, also called as farsightedness. People with this defect of vision cannot see the objects at nearby distances but can see the objects at far distance clearly. For these people, the minimum focal length is greater than 2.27 centimeters. When viewing the nearby objects, the rays will fall on the lens and these rays converge and forms an image behind the retina. So when the object is placed at least distance of distant vision, this person is not able to see the image. So the object has to be moved away from the lens such that the image forms on the retina. So to move the object away from this distance, we have to place a biconvex lens. The rays first fall on this convex lens and gets converged, and these converging rays falls on our eye lens and forms a clear image on the retina. When the convex lens is placed in front of the lens, then it forms a virtual image at point N, which is called as near point. The focal length of this convex lens must be f is equal to 25d by d minus 25. Here d is greater than 25 centimeters, so f becomes positive. So positive indicates that the lens is convex lens. D is the distance of near point. Coming to presbyopia. This vision defect is caused due to aging. Our eye lens loses the ability of accommodation. People with this defect suffers from both myopia and hypermetropia. Generally, people with normal vision, when viewing nearby objects, the lens becomes thick and so forms an image on the retina. For a person with presbyopia, the lens becomes hard and loses the ability to change the shape, so the image forms behind the retina. This presbyopia can be corrected by using a bifocal lens. This bifocal lens is formed by using both concave and convex lenses. The upper portion is concave lens, which helps us to see the far objects, and the lower portion is convex lens, which helps us to see the nearby objects. So, to correct the defect of presbyopia, we use a bifocal lens. When we go to an eye hospital to get tested for vision defects, the doctor prescribes corrective lenses indicating their power. Let us see what is power of the lens. Power of the lens is defined as the reciprocal of focal length in meter. That is, power P is equal to 1 by F in meter. SI unit of power is diopter. If the focal length is given in centimeters, then power is equal to 100 by F. For a convex lens, the power is always positive, and for concave lens, the power is always negative. So, it is understood that when the light travels from one medium to another medium, it gets refracted. Then, let us know how the light ray behaves when it passes through a prism. Already, I have explained the complete topic of prism in our channel. If you are unaware of it, link for the complete video is given in the description box. Go through the video and come back for the rest of the lesson. In that video, you have learned that when a monochromatic light is incident on the prism, it comes out as an emergent ray. The formula to find the diffractive index of the prism is n is equal to sin a plus d by 2 by sin a by 2. Now let us learn what happens when a white light passes through a prism. When the white light passes through a medium, each color selects its least time path following Fermat's principle. So, refraction of different colors takes place at different extents. This results in separation of colors forming a spectrum. This splitting of light into different colors is called dispersion. White light splits in 7 different colors called vedio: violet, indigo, blue, green, yellow, orange, red. Violet color deviates the most, while the red color deviates the least. As we know that frequency remains constant during refraction, V is equal to F into lambda, where F is the frequency, lambda is the wavelength, and V is the speed of the wave. So, V is directly proportional to lambda. That means as the wavelength increases, speed of the wave also increases. If we compare the wavelengths of 7 colors of vedio, red color has the longest wavelength and violet has the shortest wavelength. The refractive index of red is low, so it suffers low deviation. The refractive index of violet is more, so it suffers high deviation. The best example for dispersion of light is rainbow in the sky. The formation of rainbow is clearly explained in our channel. Watch the video completely to understand the formation of rainbow. Link to the video is given in the description box. Now let us understand the phenomena behind the various colors of the sky. when the sunlight of certain frequency falls on an atom or a molecule, and if the size of the atom or a molecule is comparable with the wavelength of the light, then the atom observes the light and starts vibrating. Due to these vibrations, the atom re-emits the light in all directions with different frequencies. This process of re-emission of light in all directions with different frequencies is called scattering of light. The re-emitted light is called scattered light, and the atoms and the molecules are called scattering centers. The intensity of scattered light varies with the angle of scattering. If the angle of scattering is 90 degrees, then the intensity of scattered light is maximum. See why the sky appears blue. The sky appears blue due to scattering of light. Our atmosphere contains nitrogen and oxygen molecules. Each of these molecules is comparable to the wavelength of blue light. So these molecules act as scattering centers for scattering blue light. Thus, the sky appears blue. Sometimes the sky appears white. Our atmosphere contains more water molecules. These water molecules scatter the color of other frequencies other than blue color. So all such colors of these frequency reach our eye, and thus the sky appears white. Sometimes we observe that sun appears red during sunrise and sunset. So the reason for this is again the scattering of light. The molecules whose size is comparable with wavelength of red light are very less in atmosphere. So red light scatters the least. During sunrise and sunset, the light has to travel long distance during its journey, and all colors scatter more and vanish before they reach our eye. Only the red light, which has the least scattering, reaches our eye. So, sun appears red during sunrise and sunset. And during the noon, the distance travelled by the light rays is less. Therefore, all colors reach our eye without much scattering. Hence, the sun appears white during the noon. We have come to the end of this session. Let us end the session with a small activity. So, take a solution of sodium thiosulfate and sulfuric acid in these glass beakers. So, place these glass beakers in the open space and observe the changes in the grains of sulfur. Sulfur precipitates as the reaction is in progress. At the beginning, the grains of sulfur are small in size, and as the reaction is going on, the size increases. The sulfur grains appear blue in color at the beginning, and slowly their color becomes white as their size increases. So the reason for this is scattering of light. At the beginning, the size of the grains is small because this size is comparable with the wavelength of blue light. So the grains of sulfur appears blue in color. As the size increases, the size of these molecules is comparable to the wavelength of other colors. So these molecules act as scattering centers for other colors. So the combination of these colors appears as white.